Hello everybody. In this video we are going to be looking at the solutions to the college prep electromagnetic induction homework problems 6 through 10. Let's take a look at problem number 6. We have a 35 centimeter square loop of wire consists of 14 turns. When the wire turns 90 degrees in 320 milliseconds in a 5.9 times 10 to the minus second Tesla magnetic field, what is the induced EMF in the wire? So a couple of things to note before we start unpacking this problem. We can see that the wire is turning 90 degrees, which means that it is going from a minimum value where it would be parallel with the magnetic field to a maximum value where the loop is going to be perpendicular to the magnetic field. So when I look at my change in the magnetic field, delta B, it's going to be my final minus my initial value, and if this is 0, then my delta B is going to equal my final value. So that's just something I wanted to point out here. So let's take a look and see what we're given in the problem. We are given the length of a side of the square loop, and we are told that it is a square loop that is 35 centimeters. I know I need to convert that to meters, so that's going to be 0.35 meters. And because it is a square loop, I know to find the area of the loop, I just need to square the side. So 0.35 meters squared is going to give me an area of 0.1225 square meters. The number of turns in the loop is 14. And the time it takes to turn 90 degrees is 320 milliseconds. And again, we need to convert that to seconds. So that's going to be 0.320 seconds. And the strength of the magnetic field is 5.9 times 10 to the minus second Tesla. And they want to know what is the induced EMF in the wire. So remember, for induced EMF or induced electromotive force, we are going to use this funny looking E here, or the Greek letter epsilon is really what it is. And I know that I'm going to need to use Faraday's law of electromagnetic induction to find the induced EMF. So Faraday's law of electromagnetic induction is going to be epsilon is equal to negative N times delta phi divided by T. And remember, I know that phi is equal to the area times the magnetic field. So I can replace that for phi in the equation. I'm going to get negative N times the area times the change in the magnetic field divided by the time. Now I can plug my known values into the equation, and when I do that, I should get an induced EMF of negative 0.32 volts. All right, let's try this again. You don't see this at home, but this is actually my fourth attempt at trying to narrate this problem. So let's see if I can get it right this time. Problem 7. When a single 25 centimeter circular loop of wire turns 90 degrees in 0.68 seconds in a magnetic field, an EMF of 0.475 volts is induced. What is the maximum strength of the magnetic field? So I'm given the diameter of the loop of wire, and we are told that it is a circle. So I'm given the diameter of the circle, and that is 0.25 meters. I know that in order to find the area of the circle, I'm going to need the radius. So to find the radius of my circle, I'm going to take my diameter, divide it by 2, and that will give me a radius of 0.125 meters. Now I can find the area, which is pi r squared. So I multiply pi by the square of my radius, and I am going to get an area of 0.049 square meters. I'm given the number of turns in the loop, and we are told that it is a single loop of wire, so my number of turns is 1, and I am also told that it is turning 90 degrees, so I'm going from a minimum to a maximum value. And when I do that, I know that I am inducing an EMF of 0.475 volts. And I'm turning that 90 degrees in 0.68 seconds. And I'm being asked to find the strength of the magnetic field. By the way, this is the farthest I've gotten so far. So fingers crossed, I'm going to get through this one. As with the previous problem, we're going to need to use Faraday's law to solve this. So I know that epsilon is equal to the negative of the number of turns times the area times the change in the magnetic field divided by the time. When I solve that for the magnetic field, or solve that for B, I'm going to get the negative of epsilon times T divided by N times A. Plug in my known values into the equation, and I am going to get a magnetic field of negative 6.6 Tesla. I did it! Woohoo! Problem 8. A 25 centimeter square loop of wire consisting of multiple turns is rotated 90 degrees in a negative 2.7 times 10 to the minus third Tesla magnetic field in 0.37 seconds. If the EMS induced in the wire is 3.19 millivolts, how many turns are in the loop? In this problem, we are given the length of a side, and that is 25 centimeters. So that will convert to 0.25 meters. I know that we are working with a square loop of wire. So to find the area of the square, I just have to square the length of one of the sides, and that will give me an area of 0.0625 square meters. I know that we are rotating the loop 90 degrees. So once again, we are going from a minimum to a maximum value. And the strength of the magnetic field is negative 2.7 times 10 to the minus third Tesla. It's turning the 90 degrees in 0.37 seconds. And when it does that, it's inducing an EMF of 3.19 millivolts, which is equal to 3.19 times 10 to the minus third volts. And what we're being asked to find in this problem is the number of turns. So we want to solve for N. Once again, we start with Faraday's law. We rearrange that to solve for the number of turns, and we are going to have N is going to equal negative times epsilon times time divided by area times magnetic field. Plug my values into that equation, and I am going to get a value of N of 7.0 turns. So there are 7 turns in the square loop of wire. Problem number 9. A 36 centimeter diameter loop of wire consists of 8.0 turns. As the loop turns in 84 milliseconds, an EMF of 5.5 times 10 to the minus first volts is induced. If the final strength of the magnetic field is 3.5 times 10 to the minus first Tesla, what is the initial strength of the magnetic field? First of all, let's take a look and see what we are given in this problem. We are given the diameter of the loop of 36 centimeters. Once again, we convert that to meters, and we have 0.36 meters. Because we're given a diameter, I know that is going to be a circle, and I'm going to want the radius to find the area. So the radius is the diameter divided by 2, and that will give me a radius of 0.18 meters. The area is pi times 0.18 meters squared, and that will give me an area of 0.10 square meters. I have 8 turns in the loop, and the loop is turning in 84 milliseconds. So I have to convert milliseconds to seconds. And when I do that, I should get 0.084 seconds. And my induced EMF is 5.5 times 10 to the minus first volts. Now I'm given the final strength of the magnetic field. So that's going to be my final value. Oops, let me use the highlighter here. Sorry. Let me just redo this here. So this is going to give me the final value for the magnetic field of 3.5 times 10 to the minus first Tesla. And what I'm being asked to find is the initial value of the magnetic field. Once again, we're going to start with Faraday's law, but we're going to depart slightly from what we've done in previous problems, where we have the delta B for the change in the magnetic field. Now I want to break that down into B final minus B initial, because that's going to give me my given value for the final strength of the magnetic field, and it is going to give me my initial value for the magnetic field, which is what I want to solve for. So when I rearrange this equation to solve for the initial magnetic field, I'm going to have the initial value for the magnetic field is equal to the induced EMF times the time divided by the number of turns times the area, and that product is going to be added to the final value for the magnetic field. I plug my known values into that equation, and I am going to get an initial value for the magnetic field of 4.1 times 10 to the minus first Tesla. Problem 10. A circular loop consisting of 6.0 loops takes 0.48 seconds to rotate 90 degrees in a 2.4 Tesla magnetic field. If the EMF induced in the wire is 1.59 volts, what is the diameter of the loop in centimeters? So in this problem, we are given the number of turns, which is 6. We're given the time it takes to rotate 90 degrees, which is 0.48 seconds. We are given the strength of the magnetic field, 2.4 Tesla, and the EMF induced in the wire, 1.59 volts. And we're being asked to find the diameter of the loop. Now I know in order to find the diameter of the loop, I'm going to need to know the area of the loop. So using Faraday's equation, I can solve that for area. When I do that, I'm going to get the area equals the induced EMF times the time divided by the number of turns times the magnetic field. Plug my known values into that equation, and I'm going to have an area of 0.053 square meters. So now I have the area of my loop of wire. Now that I know the area, I can use that to find the radius of the loop. And I know the area is equal to pi times the square of the radius. When I solve that for the radius will equal the square root of the area divided by pi. When I do the math for that one, I'm going to have a radius of 0.13 meters. I know the diameter is 2 times my radius, so 2 times 0.13 meters is going to equal 0.26 meters. And I'm asked to find my answer in centimeters, so 0.26 meters is going to equal 26 centimeters.